How can a robot determine its current position and orientation in an unknown environment? How can a map of the perceived surroundings be created and used to support the localization? These are two of the main questions in robotics, especially when talking about autonomous vehicles, and led to the development of a variety of different algorithms to solve the problem of localization. The most famous approach is probably simultaneous localization and mapping, or SLAM, whose name sums up quite precisely what it actually does. One of these SLAM algorithms, developed for systems which are equipped with a LiDAR scanner, is called LiDAR odometry and mapping, or briefly LoAM. In this video, we will have a closer look at an advancement of this framework, lightweight and ground-optimized LoAM, explain its fundamentals, question how it works, show the capabilities in example applications, and discuss its performance, especially in comparison to the original LoAM. In the end, we will have a look at the further developments and talk about how the algorithm already was and will be enhanced in the near future. This video was created as part of the seminar 3D Mapping and Geometry Processing for Underwater and Aerospace Applications at the University of Würzburg. Let's start and have a look at the original LiDAR odometry and mapping algorithm. LoAM was proposed by Zhang and Singh from the Robotics Institute at Carnegie Mellon University in 2014. As the name already suggests, we make use of a laser scanner to capture the environment. We use the LiDAR measurements to estimate the performed motion and to build up a map of the system's environment. These two steps are the basic operations performed by the LoAM framework. On the one hand, we use a shift between the two consecutive LiDAR scans to determine the transformation and therefore estimate the motion and simultaneously apply the determined transformation to distort the captured point cloud. On the other hand, we match the distorted point clouds and register them into a global map using a suitable registration algorithm. The results from these two steps are fused and thereby enable a ground vehicle to perform quite accurate and reliable but simultaneously fast pose estimation. But why do we now need LeGO-LOAM? What functionality is added by harnessing LeGO-LOAM instead of the standard framework? To answer this question, we will at first think about the challenges which the original LoAM encounters. They are caused by three different problems. This figure clarifies the difficulties and shows how they affect the pose estimation process. Firstly, LoAM has to handle the problems that occur from the physical properties of small unmanned ground vehicles. Usually, these small robots are not equipped with huge suspensions and moving on variable and rough terrain. In combination with high velocities, these properties can complicate measurements like LiDAR scans. The robot moves quickly along its path and LiDAR suffers from the sudden movements caused by the terrain. These disturbances cannot be sufficiently tracked, which results in distorted point clouds. The second aspect limiting the performance of LoAM are the limited onboard computational resources. Huge amounts of data primary point clouds have to be processed by the system. Usually the computational requirements for processing point clouds do not play a major role due to the availability of hardware which provides sufficient capabilities. In the context of small-scale ground vehicles, however, this is a problem. The mobile robot is intended to work with low power and only minimal computational resources. Simultaneously, it has to process the captured data in real time to work reliably and produce the estimations for the current pose. As a consequence, the number of processed points has to be chosen with respect to the available resources. The amount of data therefore is reduced by considering only a limited number of points for pose estimation. This unavoidably leads to inaccuracies and uncertainties in pose estimation. The third aspect LoAM is challenged with are too noisy or too monotonous environments. Especially in forests or on grassland, the number of unreliable features can be very high. Leaves of trees or grass blades are moving in the wind and continuously changing its pose. Also, each look like the other, which can cause confusions between the individual objects. If features extracted from them are used for motion estimation, the result will be inaccurate and distorted. So, it's important to not assume unstable features being reliable. The effect always can be seen when using objects which might change its position or orientation over time to extract features. Not only the consequences of environments with moving objects, but also of those with monotonous structures are problematic. If similar objects occur repeatedly next to each other, extracted edge and planar features could possibly be matched faulty. If no objects at all are available, for example in case of just a blank and even wall, we could potentially run in a situation where no helpful features are provided. So if the environment is inappropriate and does provide no or mostly unreliable features from moving or repeating objects, LoAM gets difficulties with erroneous matching of consecutive LiDAR sweeps. All three described problems have one thing in common. In the end, they lead to erroneous motion estimation and faulty maps, and therefore prevent LoAM from performing an accurate and reliable pose estimation in certain more advanced situations. This is obviously something we don't want to accept. The solution for these problems: LeGO-LOAM. LeGO-LOAM can be summarized as a method for reliable real-time 6-degree of freedom pose estimation and mapping for unmanned ground vehicles equipped with a 3D LiDAR to be implemented on a small-scale embedded system. It was proposed and realized by Chen and Englert from the Department of Mechanical Engineering at the Stevens Institute of Technology in 2018. LeGO-LOAM builds on the foundation of LoAM. It improves its performance primarily in the previously described areas and can be applied in all systems where LoAM can be implemented. Some steps are adapted and an extra module added, but neither the basic functionality nor the input and output nor hardware of the used system are altered. LEGO stands for lightweight and ground optimized, but what does this exactly mean? The properties lightweight and ground optimized both refer directly to solutions for some of the described problems of the LoAM algorithm. LeGO-LOAM is described as lightweight because it is able to perform real-time pose estimation, although only low computational capabilities are available. The property ground optimized stems from the way LeGO-LOAM processes the captured point clouds before the motion estimation. In a segmentation step, ground point extraction is applied to the recorded point clouds. The estimated ground points later are considered for the extraction of the so-called planar features. This second aspect helps LeGO-LOAM to be more resilient against unstable features resulting from moving ground objects like grass blades. The details on how the performance is increased are specified in the upcoming system module descriptions. But first, we will take a quick look at the used robotic and instrument hardware. Both LoAM and LeGO-LOAM were developed and tested with an unmanned ground vehicle. Here we can see the ClearPath Jackal UGV, which was used for testing the LeGO-LOAM system. On top of the robot, the Velodyne VLP16 LiDAR is mounted. The VLP16 has a 16-channel sensor, which provides a vertical angular resolution of 2 degrees and a horizontal angular resolution of 0.1 to 0.4 degrees based on the chosen rotation rate. Its field of view measures 30 degrees vertically and 360 degrees horizontally. In addition to the LiDAR, an IMU is installed on the system. This is not mandatory but helps the algorithm to get useful initial guesses, as we will see later. The LeGO-LOAM developers used the CH Robotics UM6 orientation sensor, a low-cost IMU, for this purpose. For the computation, two different devices are tested: the NVIDIA Jetson TX2, an embedded device with an ARM Cortex-A57 CPU, as well as a regular laptop with an i7 CPU, which matches the processor employed in the original LoAM, are used to test the performance and abilities of LeGO-LOAM in different experiments. Now we want to look at the actual system setup and the different components' functionality. The LiDAR sensor captures the environment and produces a measurement, or more precisely a point cloud. This point cloud is pre-processed by the segmentation module, which determines the points belonging to the ground or large objects and filters out points from small objects representing probably unreliable features. In the feature extraction step, points representing prominent features are determined and extracted utilizing a measure for their roughness. Depending on this roughness value, the points are categorized as either planar or edge features. These features are used to determine the system's movement in the LiDAR odometry module by finding correspondences between the features of the current and the previous captured point cloud. The estimated transformation is used to distort the current point cloud and afterwards sent to the transformation integration and the LiDAR mapping modules. The LiDAR mapping module holds a global point cloud of the already explored environment. The extracted features are used again to register the newly captured and distorted point cloud into the global map. The registration process conducts another transformation estimation. Both estimations from the LiDAR odometry and the LiDAR mapping module are combined in the last step, performed by the transform integration module. The final pose estimation is calculated and afterwards published as the final result. The LiDAR odometry module already outputs a transformation estimation. So why do we need to perform the LiDAR mapping step and calculate the transformation a second time before we publish the pose estimation? LeGO-LOAM has to work time efficient and accurate at the same time. To achieve real-time performance while providing accurate results, the pose estimation problem is divided across two modules. LiDAR odometry only works with the point cloud from the previous and the current LiDAR measurements. Therefore, it can be executed at a high frequency of 10 Hz. The determined transform is not very accurate because only a few points and not the complete map is considered. LiDAR mapping, on the other hand, includes more points from all the surrounding point clouds that were captured previously. As a consequence, the map registration of the current LiDAR measurement takes its time and can be executed only with a frequency of 2 Hz, but the resulting transformation estimation's accuracy is significantly higher. Combining both algorithms provides a fast and simultaneously accurate method for determining the transform between the previous and the current measurement with a frequency of 10 Hz. Now, let's start talking about the framework modules in more detail. We begin with a closer look at the segmentation step. In the rest of this video, we will refer to a full LiDAR scan as a sweep. So every time the LiDAR completes one time of scan coverage or made a 360-degree turn, we call it a new sweep. The point cloud captured in the current sweep K is denoted as PK. Before executing the actual segmentation, we project the point cloud PK on a so-called range image. The 3D point cloud data is converted into a 2D image. Each valid point Pi of the current point cloud gets assigned to a range image pixel. The Euclidean distance between the LiDAR scanner and the captured point or depth information is saved as Ri. Then ground point extraction is applied. We determine the points representing the ground and label them accordingly. All the other points are further processed by the actual image-based segmentation. The non-ground points are grouped into clusters and assigned with a unique label. The clusters containing less than 30 points are omitted to exclude small objects which tend to expose as unstable features and noise from further processing. Therefore, only points representing large objects which can be used for reliable feature extraction and the previously extracted ground points are preserved and saved in the output range image. Besides the Euclidean distance Ri, the assigned label is also memorized. It denotes for every pixel if the saved point is part of the segmented cluster or part of the ground. This will be relevant in the following step, the feature extraction. In the following, we use the terms point cloud and range image interchangeably. In this context, they only address the internal representation and do not affect the actual data processing. For feature extraction, we look at every single point in the range image considering its local neighborhood. For a point Pi, we take a set of continuous points S from the same row in the range image into account. Now we can calculate the roughness of point Pi dependent on the neighboring points in S, using the sum of differences between the distance Ri and all Rj, with j being the indices of the points in S normalized to Ri, and considering the total number of points in S, we determine the roughness value C. LeGO-LOAM differentiates between edge and planar features. For the decision how a point is classified, we define a threshold for C. The point Pi is categorized either as a planar feature if its roughness value is smaller than the threshold, or as an edge feature point if it is bigger than the threshold. To extract the features evenly from the whole scan, we divide the range image in 6 equal-sized sub-images with each covering a window of 60 degrees of the environment. From every sub-image, a predefined number of edge and planar features is extracted. In the further processing, we utilize the notations f sub e, f sub p, double f sub e, and double f sub p for denoting the sets edge and planar feature points are assigned to, whereas k represents the current sweep's index. Later, the features from the f to the k sets, so the one of the current sweep, will be matched against the features from the double f to the k-1 sets, the ones of the previous sweep. But this will be explained in more detail in the next module. Anyway, the set f sub e to the k is filled with the 2 points from each sub-images row for which the highest roughness values that have to be bigger than the threshold c were calculated, whereas the set f sub p to the k comprises the 4 points with the smallest roughness value, which is smaller than the threshold c of each sub-images row. For the edge features, only the points that are not part of the ground are taken into account. The planar features are extracted from the ground exclusively. If no points matching the criteria of being smaller or bigger than the threshold, the sets stay empty. The sets f sub e and f sub p to the k analogously maximally contain the 40 and 80 most and least rough features from every sub-images row. For the set f sub p, however, we consider both ground and cluster points. It holds that f sub e is a proper subset of f sub e and f sub p is a proper subset of f sub p. In contrast to LeGO-LOAM, the original LOAM does not apply a segmentation step, therefore no ground area is extracted and no points are clustered or labeled. The definition of the sets f sub e and f sub p is similar in LOAM. Because the differentiation between ground and cluster points is not possible, the edge and planar features are extracted both from the same pool of candidates. The sets f sub e and f sub p does not exist in LOAM. LeGO-LOAM does not change the idea of how features are extracted, but improves the performance by more effective feature handling. Here we can see the point cloud after being processed by the first 2 modules. A shows the point cloud directly after capturing. B illustrates how the ground point extraction step segregates the ground area and how the segmentation clusters the other points and discards noise and small objects. In C and D is depicted how the point cloud looks like after feature extraction. The edge features of the sets f and f are marked in blue and green respectively. The planar features of the sets f and f are represented by the yellow and magenta colored points. Now we want to talk about how we can use these condensed feature point clouds to determine the robot's motion in pose. So let's have a look at the LiDAR odometry module that estimates the transformation between the previous and the current sweep. In the LiDAR odometry module, we want to determine how the robot translates and rotates during the current LiDAR sweep. For this reason, we are looking for correspondences between the features extracted from sweep k and the ones extracted from sweep k-1. Or more formally, we want to find corresponding points for the features in the sets f to the k in the sets f to the k-1. The feature sets f sub e to the k and f sub p to the k are dynamic because the saved features are continuously updated until the current sweep k finishes and the point cloud is completely captured. Let's assume the LiDAR sweep just begun. The feature sets are empty, but then steadily filled and updated by the feature extraction module while data is recorded. To find correspondences, LeGO-LOAM utilizes point-to-line and point-to-plane matching. For an edge point pi in f sub e to the k, the corresponding edge line defined by 2 points is searched in the closest neighbors of pi in the set f sub e to the k-1. For a planar point in f sub e to the k, a corresponding planar match represented by 3 points is searched in the closest neighbor features of the set f sub p to the k-1. We know that all features in f sub p to the k belong to the ground. Therefore, LeGO-LOAM only has to consider those points in f sub p to the k-1 which are also labeled as ground points. The robot moves while the current sweep is recorded. To obtain a realistic image of the environment despite this movement, the recorded point cloud pk, i.e. the extracted features f sub e to the k and f sub p to the k, have to be projected to a fixed pose. In LeGO-LOAM, the pose the LiDAR holds at the beginning of the current sweep k, so at the time tk, is set as this reference point. Simultaneously, the feature sets f sub e and f sub p of the previous sweep k-1 are projected to the same point in time, so that we are able to find correspondences that make sense. Now, for all the features from the sweeps k-1 and k, it can be assumed that they were recorded from the same position and orientation and at exactly the same point in time. But one question remains: how do we project the feature points to the initial LiDAR pose when we don't know how the robot actually moved. The estimation of this transformation and therefore the current pose is the purpose of this whole framework. We can't know it already. The answer to this question is quite simple. We just determine the pose transformation by finding its inverse, the projection. The problems are equivalent, so resolving them is one. We assume that the robot moves with constant angular and linear velocities during a sweep. We're looking for the transformation capital T to the k, which equals the robot's whole motion during sweep k and is the motion between the times tk and tk plus 1. We define capital T to the k of t as the transformation between tk and the current time t. We initialize the transformation's translational and rotational parameters with zeros. From the already recorded part of the sweep, we extract features and project them onto the initial LiDAR pose using capital T to the k of t. A feature point which was recorded at time tki is projected to tk by linear interpolation of the transformation as depicted here. This is only possible because we assume the constant velocities. The features from f to the k would now align with the correct corresponding features from f to the k minus 1 if the used transformation capital T to the k of t describe the as yet performed robot's motion exactly. In reality, this case does not occur due to the not perfect constant velocities and measurement inaccuracies. But we can approximate the transformation still very well. Because we initialized capital T to the k of t with default values, it is very unlikely that we hit a good approximation in this first iteration. To improve the guess and obtain a transformation which is closer to the real one, we try to minimize the distance between the correspondences of the sets f to the k and f to the k minus 1 and update the transformation guess. With this new transformation guess, we again look for correspondences, because some of them must probably have changed because of the updated transformation, and then again minimize the distance between the features from both sets from which we assume that they represent the same object. This optimization loop is realized with the Levenberg-Marquardt method. We apply the Levenberg-Marquardt optimization term one time in each iteration. These steps are repeated over and over till the optimization converges, i.e. the found correspondences and therefore the minimal distances, and the resulting transformation guess do not change anymore, or a previously defined number of iterations is met. While the LiDAR sweep is going on, the LiDAR odometry module is called several times. The feature sets f sub e and f sub p are updated at every call because the feature extraction module may have found more rough or dominant features in the meantime that replace the previously stored features. The LiDAR odometry module is executed with a frequency of 10 Hz, which is equivalent to 5 times per sweep. The transformation optimization is therefore also performed 5 times till the end of the sweep is reached. As initial guesses for the transformation in a new execution, the transformation determined in the previous execution can be used. While at the beginning of a sweep we only can use default values, i.e. zeros, we now have a more accurate initial guess for the transformation parameters. When the sweep finally is finished, we obtain an estimation for the transformation which is optimal with respect to the extracted features. The transformation is applied to the feature sets f sub e to the k and f sub p to the k to project them to the initial LiDAR pose of the following sweep k plus 1, i.e. to the time tk plus 1. Then the next sweep's transformation, capital T to the k plus 1, can be determined by the next call of this module and the previous steps executed again with the just projected feature sets f sub e to the k and f sub p to the k. The LiDAR odometry module in LoAM and LeGO-LOAM works very similar. Nevertheless, there are small differences which are important to understand. Firstly, as already mentioned previously, the f sets do not exist in LoAM. The correspondences for the features from f sub e and f sub p to the k are searched by determining the nearest neighbors in the raw point cloud data from sweep k-1. Another difference is how the Levenberg-Marquardt optimization method is implemented and applied. In both frameworks there exist expressions for determining the distance between the features in the sets f and its correspondences. In LoAM, these expressions are combined in a single distance vector holding both the distance of edge and planar features. LeGO-LOAM does not combine the terms for the distance of edge features and planar features. They are treated separately. The applied Levenberg-Marquardt method is internally realized in two stages, by minimizing the distance between the planar feature sets f sub p to the k and double f sub p to the k minus 1, the translation in z direction, and the roll and pitch rotation angles of the transformation matrix are determined. In the second step, the edge feature set's distance is optimized and the translation in x and y direction plus the yaw rotation angle are calculated. In the second stage, the possible outcomes are necessarily constrained by the parameters already determined in the first stage. LoAM and LeGO-LOAM both offer the possibility to use the data of an IMU to obtain an initial guess for the transformation at the beginning of a new sweep. In the first execution of the LiDAR odometry module in a new sweep, no default zeros have to be inserted anymore. Instead, the IMU data is leveraged to get a more accurate guess and decrease the computational efforts by reducing the number of iterations the Levenberg-Marquardt method needs to converge. However, the IMU is optional and the algorithm still works without this additional sensor. The determined transformation estimation could now be used for estimating the pose in the transformation integration module. But as already mentioned, we want to correct possible erroneous transformations to obtain reliable pose estimation. Therefore, we further process the extracted features and register them into a global point cloud map in the LiDAR mapping module. The LiDAR mapping registration process enables correction of the pose estimation while building up a map of the visited environment. The mapping module is called once per sweep and processes the whole data which was captured during the last sweep. LiDAR mapping gets the transformation calculated in LiDAR odometry as input. The points from the just finished sweeps feature sets double f sub e to the k and double f sub p to the k are projected to the initial LiDAR pose of the next sweep k plus 1 in LiDAR odometry as described before. This projected and therefore undistorted point cloud is also passed from LiDAR odometry to the LiDAR mapping module. A global point cloud map Q, which includes all the features extracted from the previous recorded point clouds, is saved. The inputted transformation parameters of the last sweep in combination with a transformation capital T sub q to the k minus 1 between the LiDAR initial pose, which equals the end pose of the previous sweep, and the global origin obtained from the previous iteration are now used to align the points from the projected feature sets with this global map. This is a prerequisite for the registration process, which works similar to the matching method in the LiDAR odometry module. The difference is that the point cloud which is being matched consists of features from the sets double f sub e to the k and double f sub p to the k. The existing map q to the k minus 1 against which the point cloud is matched can comprise all the features from the sets double f sub e and double f sub p of the previous sweeps. Which features are used for finding correspondences depends on our current LiDAR sensor position. Only the points which were recorded from a LiDAR position within 100 meters of the estimated current sensor position are considered for the matching process. The sets f sub e and f sub p do not play a role anymore. Then again, the Levenberg-Marquardt method is applied for optimization. As before, the correspondences are found using the point-to-line and point-to-plane methods. The distance between the map Q and the newly added points from the last sweep is minimized, which results in an updated transformation T sub Q to the K. This optimization procedure is again repeatedly executed till it converges or a maximum number of iterations is reached. The obtained transformation is then used in the transform integration module. The LiDAR mapping module of LoAM and LeGO-LOAM differs only in the manner the undistorted feature sets are obtained and the point cloud map is stored. Because in LoAM the feature sets double f sub e and double f sub p do not exist, the points have to be extracted in an additional step from the undistorted point cloud, which contains all of the captured points. LoAM stores the global map Q as just one single point cloud. LeGO-LOAM, on the other side, stores the feature sets double f sub e and double f sub p of all previous sweeps individually. Additionally, the information on the pose of the sensor when capturing these sets is stored in LeGO-LOAM. We've just used it to filter all the features that were captured from sensor positions further away than 100 meters from the current one. But saving the pose information has another advantage. LeGO-LOAM adds another method for matching captured point clouds against the already mapped features. It integrates pose graph SLAM. The stored sensor poses represent the nodes in our pose graph. The corresponding feature sets f sub e and f sub p of the respective sweeps are the sensor measurements. The pre-aligned pose of the new measurement is added to the pose graph. For the edges or constraints between the recently stored nodes for which zero drift can be assumed, because they represent the sensor poses of the lastly recorded sweeps and the one we want to add for the newly captured data, we utilize the transformations obtained from the Levenberg-Marquardt optimization as before. Then loop closure detection is performed to simultaneously match the new features against all the previous sweeps features using ICP. The pose graph with all the constraints from the determined transformations and the loop detection is then sent to an optimization system. We use the obtained optimized sensor pose in the transform integration. The loop closure integration improves the system's performance, as we will see in the experiments. The pose transformations from both the LiDAR odometry and LiDAR mapping module are in a final step combined by the transform integration module. The LiDAR odometry estimation arrives, as already mentioned, with a frequency around 10 Hz. The LiDAR mapping estimation is obtained with a frequency of 2 Hz and therefore used to correct the odometry output twice every second or once per sweep. Finally, the fused pose estimation is returned and the system fulfilled its aim, the localization of the robot and creation of a map of the environment. After all the theory, we want to have a look at some applications of the framework. The experiments presented hereafter were all conducted by the team that invented LeGO-LOAM. For demonstrating the basic functionality, they let the robot drive through different outdoor environments. The first one is a forest trail, the second one an area on the university campus covered with vegetation. The performance of LOAM and LeGO-LOAM with regard to feature extraction is compared qualitatively. In the video on the bottom left, we can see how LOAM processes the captured data and selects features. The video on the right shows how LeGO-LOAM handles the situation and extracts the features from the recorded LiDAR point clouds. The advantage from extracting features of a point cloud which was previously segmented is obvious. In LeGO-LOAM, the extracted features represent mostly large objects or the ground and include less points caused by noise or unreliably moving objects. LOAM, on the other side, extracts especially edge features from the tree leaves or grass on the waysides. The consequences can be seen by observing how the map of the university campus is built. Due to the inaccurate feature matching in the odometry and mapping modules, the map, which was created with LOAM, represents the environment less precisely and accurately. This can be seen looking at this tree. LeGO-LOAM recognized it as one object. For LOAM, the tree consists of 3 different ones next to each other. For quantifying the performance differences, 3 further experiments are conducted. The first experiment is a demonstration of the low drift pose estimation while driving through an urban environment. The robot moves smoothly without aggressive yaw maneuvers, usually stable features are available and the terrain is even with only smooth asphalted roads. The initial and final position of the robot on this loop track is compared. If the system worked without errors, these should be identical. For LOAM and LeGO-LOAM, the achieved low drift pose estimation works well. The difference between both poses is small. The created map shows a few inaccuracies, but represents the environment still decently. The second experiment is executed in the same environment, just the chosen trajectory slightly differs from the previous path. The robot drives across a sidewalk with stable features like a wall and pillars on the one side, and a noisy environment with grass and trees on the other side. The pose estimation performed by LOAM suffers from these adverse conditions. LOAM is not able to decide what features are reliable and therefore also uses the unreliable ones extracted from grass blades and tree leaves. In LeGO-LOAM, with its additional segmentation module and the additional constraint in feature extraction that edge features may not be part of the ground, is able to filter these unreliable points. The map deviation is quite obvious. This misalignment can also be measured by comparing the initial and final poses again. In the table, we can see the deviation between these poses. The on-average accuracy of LeGO-LOAM was higher by an order of magnitude. The third experiment of this series focuses on the demonstration of capabilities on trails in a forest environment. The robot is driven in challenging terrain on different subgrounds. Dirt-covered trails alternate with asphalt and grass-covered ground. The robot needs 35 minutes to finish the loop paths and has to handle an elevation change of about 90 meters. Again, the initial and final poses are compared. The misalignment in LoAM can easily be recognized. The translational error amounts to 62.11 meters and a rotational deviation of 8.50 degrees is measured. LeGO-LOAM performs significantly better with errors of 14.87 meters and 7.96 degrees. The paths of 10 runs obtained by LoAM and LeGO-LOAM are shown here. The consistency of the LeGO-LOAM paths is significantly higher than of the ones that were determined with LoAM. These experiments impressively showed how LeGO-LOAM is superior to LoAM, but the performance advantages are not limited to the accuracy. The number of processed features and calculations is reduced and the overall processing velocity increased. This table shows the number of extracted features for an example scenario. The segmentation step reduces the number of points in LeGO-LOAM significantly. For the extracted feature sets, this means a reduction in size by 29% for the set f sub e to 72% for the set f sub p. The number of iterations to the Levenberg-Marquardt optimization in the LiDAR odometry module converges does not really differ. Indeed, LeGO-LOAM uses the enhanced two-step optimization, but the overall iteration number is comparable to LoAM. The computational time savings in the LiDAR odometry module also come from the reduced number of features. Less features to be processed lead to less calculations that have to be executed. We obtain a runtime shortening by 34 to 48%. This table shows the runtime comparison of all the modules performed in LoAM and LeGO-LOAM respectively. The additional segmentation step certainly takes some extra calculation time, but the savings in all the other modules, though, overweigh this by far. The higher velocity is especially relevant with regard to the real-time capabilities. It can affect the accuracy secondarily because no sweeps have to be skipped or omitted to guarantee punctual estimations. In the last experiment, the loop closure functionality of the LiDAR mapping module is tested. It is demonstrated using the Kitty dataset from the Karlsruher Institut für Technologie. The iterative closest point algorithm is leveraged for adding constraints between the nodes in the pose graph. The subsequent optimization is realized with the ISIM2 algorithm. Because the Kitty dataset was recorded with another LiDAR scanner than the one which was used in the previous explained experiments, the number of points has to be reduced so that the amount of data to be processed is comparable to the previously captured point clouds. Every time the robot reaches a location it already visited, a loop closure is detected and the estimated poses and therefore the map are corrected accordingly. Especially while traveling long paths, the SLAM algorithm with loop closure is a good way to minimize the pose drift and correct probable errors afterwards. In LoAM, no loop closure functionality is implemented because of its constrained performance. The processing speed is not high enough to provide SLAM with loop closure in real time. After comparing LoAM and LeGO-LOAM with regard to their performance and capabilities, we now summarize the main differences between both frameworks. LeGO-LOAM applies the additional segmentation step to preprocess the captured point cloud. Clusters are defined and labeled, points from small objects and noise are largely filtered out, ground points are extracted, and the point cloud is converted to and stored as a range image. In the feature extraction module of LeGO-LOAM, edge and planar features are determined in the segmented and therefore cleaned and reduced point cloud, considering whether the points were assigned to the ground or to objects. Additionally to the sets f sub e and f sub p which are extracted in LoAM, LeGO-LOAM comprises the sets f sub e and f sub p, which include more feature points and play a major role in the following modules. In the LiDAR odometry module, the features from the sets f sub e and f sub p are matched towards the point cloud from the previous sweep. While LoAM takes all the points from the previous sweep into account, LeGO-LOAM only considers the features from the sets f sub e to the k-1 and f sub p to the k-1 that were extracted from the previous sweep for finding correspondences. The labels that were assigned in the segmentation process are also used to decrease the amount of candidate points for possible correspondences because ground points only should be matched towards ground points. For the actual matching procedure and the determination of the post-transformation parameters, both systems apply the Levenberg-Marquardt optimization method. LeGO-LOAM, however, executes this optimization in two steps and processes the planar and edge features one after the other, while LoAM combines all the feature correspondences in a single distance vector. The LiDAR mapping module profits from the previous extraction of the feature sets f sub e and f sub p as well. In LoAM, features from the new point cloud has to be extracted. In LeGO-LOAM, the already determined feature sets are utilized. LeGO-LOAM simultaneously profits from the way the global map is stored. While LoAM holds just one large point cloud map in memory, LeGO-LOAM stored the feature sets of all the registered sweeps, including the pose of the sensor when the scan was taken. This enables LeGO-LOAM to apply PostgreSQL for the global map registration process and benefits from the ability to perform loop closure detection. All these improvements cause a measurable increase in LoAM's performance. The attributes lightweight and ground optimized sum up these changes and enhancements very well. At the end of this video, we want to take a look in recent past and future and find out where LeGO-LOAM is deployed, plus how it was further refined since its first proposal in 2018. A team from the China University of Mining and Technology worked at the application of LeGO-LOAM for the mapping of underground coal mines. They developed different extensions to optimize the LeGO-LOAM system and make it more reliable for the underground use. In 2021, they published the idea of leveraging the scan context algorithm for loop detection. While LeGO-LOAM uses ICP only based on the Euclidean distance for the loop closure and point cloud registration, this adapted system called LeGO-LOAM SC relies on the additional application of so-called egocentric spatial descriptors. These descriptors give a good initial estimate for the successful application of ICP and enables reliable loop detection and closure even in unstructured environments. Experiments using the Kitty datasets show that map accuracy and pose estimation are improved. At the same time, computational resources and processing time are saved. The same group proposed another advancement of LeGO-LOAM in 2022. LeGO-LOAM SM leverages the segmatch algorithm for loop detection and therefore starts at the same point as the previous optimization. In this approach, the standard ICP method is applied as usual. Afterwards, further constraints are searched in a second ICP application using the results of the segmatch algorithm. Segmatch uses segments instead of local or global descriptors for place recognition. It does not rely on assumptions regarding perfect segmentation or objects and therefore is applicable in many environments. LeGO-LOAM SM achieves better performance than LeGO-LOAM regarding the accuracy and the overall consistency, which directly leads to more accurate maps and better pose estimations. Applied to the Kitty dataset, the trajectory determined with LeGO-LOAM SM coincides better with the ground truth and the occurring drift is reduced. The system was applied successfully in a simulation of a narrow underground coal mine environment and achieved more convincing results than the unmodified standard LeGO-LOAM system. Another advancement of LeGO-LOAM was proposed by a group from the Korea Advanced Institute of Science and Technology. They developed PAGO-LOAM, which is characterized by its higher robustness. The ground segmentation method used in LeGO-LOAM is replaced by a method called patchwork, which performs successfully in complex and uneven urban environments. Experiments with the Kitty dataset show the better performance of PAGO-LOAM, especially in difficult rural scenes characterized by an uneven ground and with a steep slope. Both the translation and rotational errors are reduced when applying PAGO-LOAM instead of LeGO-LOAM on the sequence 2 of the Kitty dataset. In the other sequences, here sequence 5 is depicted, only small or no significant optimizations were caused by using PAGO-LOAM instead of LeGO-LOAM. A group from the School of Mechanical Engineering Shanghai developed an improved LeGO-LOAM method based on outlier points elimination. The advancements are implemented in the segmentation and feature extraction steps. Overall, 4 classes of points are eliminated: points which are too close or too far from the LiDAR scanner and points which belong to moving objects are filtered during the segmentation step. Points whose reflection intensity or distance is significantly higher or lower than those of the neighboring points, and points which are located on a plane with an angle near 0 or 180 degrees to the LiDAR device are then eliminated after the feature extraction. This pre-filtering of features enhances the point cloud before it is used in the odometry and mapping steps. The remaining feature points more likely belong to static objects, which are captured in multiple sweeps and are stable and reliable. The impact on the system's performance is also measurable in the simulation with the Kitty dataset. The translational inaccuracies are reduced, especially the error in vertical direction is decreased. The generated map reproduces the environment with clearly outlined objects. The outlier elimination LeGO-LOAM is therefore another simple and plain way for improving LeGO-LOAM. These 4 examples show that the presented framework, despite the fact it already works quite reliable, still has some optimization potential. The algorithm's advancements are all applied in different modules or at different stages in LeGO-LOAM. From segmentation to feature extraction to LiDAR mapping, the possibilities for further refinements are diverse. LeGO-LOAM was introduced 6 years ago and it is still used in various applications and enhanced for different systems and contexts. Certainly, further developments and adaptations will follow. The SLAM problem, which is solved in LeGO-LOAM, will always be a recent topic in robotics, especially algorithms using feature extraction methods based on convolutional neural networks or searching for correspondences, loop closures, and segmenting images using other deep learning methods could improve the performance of SLAM algorithms and are predestined to be combined with LiDAR odometry and mapping. So, let's stay tuned for further developments and new ideas in this field of research, and probably we will trip over LeGO-LOAM still a number of times in the upcoming future.